I decided to go ahead and make a short video where I briefly talk about and then do some examples of finding horizontal and vertical asymptotes. This is really not a very difficult topic, and sometimes the way the book may teach it may confuse students, and I try and teach it in a way that, at least in my mind, is easiest to understand. So I'm not going to do a lot of teaching. I'm going to do mainly examples, but let me just give an overview of what's going on here. So horizontal and vertical asymptotes, first they're involved in graphing and then also equations. So let me first explain to you what asymptotes are in terms of a graph, and then we'll see how that relates with the equations. Horizontal and vertical asymptotes on a graph will be indicated by dashed lines. So for the horizontal, you understand horizontal means straight across, vertical straight up and down. So in other words, if I draw, let me just make up one. I'm going to have a horizontal asymptote of y equals 2. So I go to y on my y-axis at y equals 2. And I draw a horizontal line, and I label it y equals 2. If you recall, the equation of a horizontal line on a graph is written this way. Whatever the value of y is, y equals 2. And let's say, for instance, I have a vertical asymptote at, say, x equals -1. So vertical asymptote x equals -1. Now normally on a graph, when you have these dotted lines, most of the time when you draw your graph, your graph cannot cross or touch these dashed lines. Now there are a few exceptions. Occasionally you'll have a graph where you can cross an asymptote if it's here near the center of the graph. But for sure, when you start moving far away from the origin, your graph is not going to cross or touch those lines. As a matter of fact, I'm just going to draw an example of what could be a graph for this setup. This might look something like this. This is very typical of the kinds of graphs you might see. So because of the vertical asymptote, you see from side to side, the graph is actually two separate sort of pieces or parts. And even because of the horizontal asymptote, it's separated. So you notice these graphs, first of all, it starts out here at -infinity. The graph gets very close to the asymptote, but it will never ever touch the asymptote. And now as it comes closer to the center of the graph, I begin to hit this asymptote, and that's why it turns up. And once again, as we go farther and farther up, the graph gets super close to the asymptote, but it will never actually touch or get to this asymptote. And the same way down here. As you go down, the graph gets very close to the asymptote, but it's never ever going to touch it. And as my x gets larger and larger, the graph gets very close to the asymptote, but never touches it. So this is how, let me draw one more example. Sometimes they can get pretty complicated. Let's just say, for instance, I'll draw a couple of, in this case we have two vertical asymptotes. And maybe the horizontal asymptote is just it. So for the asymptotes, this one is at x equals 1. This would be x equals -1. This one would be y equals 0. So something like this I've seen before. You might have a graph like this. So once again, normally you cannot cross or touch the asymptotes. So maybe you would go like this. And then maybe so this is something you might see. In this case, the graph has like 3 parts. Now, this and this we've talked about before, but what's going on in the center is a little different because we have the asymptote here, and now here's a case where actually this graph is going to cross this horizontal asymptote. So that will happen sometimes. Once I said it, near the center of your graph, there can be an occasion where the graph will cross an asymptote. But you can see here the asymptote at x equals -1 and at x equals 1, the graph sort of tracks it. So that's what asymptotes are in terms of physically seeing them on a graph. Now, the thing we're going to do is we're going to be given some equations or some functions, and we're going to be asked to find horizontal and vertical asymptotes. Now, by the way, there is one more type of asymptote. Let me just mention it, although I'm not going to do any problems. An oblique asymptote is where there will be times where you have an asymptote that's sort of like at an angle. So maybe you would have 2 asymptotes like this. So what happens is the graph is going to track or be very close to this asymptote, but never touch it. So occasionally you might have, so this is a vertical asymptote. This, since it's not horizontal, it's actually at an angle, they call this an oblique asymptote. Now we're not going to cover these now, but you probably will have heard of those or you may come across those. So here's what I'm going to do. Let's look at how, if we're given a function, matter of fact, here's the first problem I'm going to work through. Now, normally these horizontal and vertical asymptotes happen for rational functions. Rational functions mean a function is like a fraction. So we're given a function, and we're asked to find the asymptotes. And that means both vertical and horizontal. So we're not going to even necessarily graph it. We could graph it, but for now we just want to find it. So a vertical asymptotes are typically x equals something, right? Because vertical asymptotes, horizontal will be y equals something. We figure out vertical and horizontal asymptotes separately. It's like 2 separate problems. Let's do vertical asymptotes first. Very straightforward. And if you remember, this is going to look very similar to what we do when we try and determine the domain of functions. It's going to be exactly the same, because what I'm going to do is to find the vertical asymptotes, you set the denominator. Oh yeah, sorry, I should have left it that way. Set denominator equal to 0 and solve. And when you solve this, your solutions are going to be your vertical asymptotes. When we say set denominator equal to 0 and solve it, another way of saying that is what value for x will cause the denominator to equal 0. These two things we're saying the same way. Sometimes we'll have problems where we want to sort of think of it like the first one. You actually want to take that denominator so equal to 0. Sometimes you can look at a problem and just ask yourself what value of x would cause the denominator to be 0. And actually, for this problem, the second way is the easiest. The key is vertical asymptote. The only thing that's going to affect a vertical asymptote is the denominator. I do not care what is in the numerator. I don't care what's in the top of the fraction. Only what's in the bottom is going to determine the vertical asymptote. So in this case, I say, well, what value of x would cause the denominator to equal 0? Obviously, if x is -4, then the denominator is going to be 0. There's my vertical asymptote. To think of it another way, I could have taken the denominator and set it equal to 0 and solve this, right? If you solve this, so vertical asymptotes, absolutely, very straightforward and very easy. Basically, you ask yourself, what values of x would cause the denominator to be 0? Or if you need to, you take the denominator, set it equal to 0, and solve it. So that's the first one, very straightforward. Horizontal asymptotes, a little more involved, but once you understand how to work them, not very hard. First, let me give you the steps. And I'll explain what this means in a minute. Reduce top and bottom to what I call the leading term. The leading term means the whole key to what the leading term is what you're looking for, the largest exponent on the variable x. Let me just explain leading term. 2x squared minus x plus 1. Very typical polynomial. If I say I want to reduce this to the leading terms, what do? I see which term has the largest exponent on the variable. So I've got exponent of 2 here, exponent of 1. So this is a large, this is my leading term. In a sense, all I'm doing is I'm eliminating everything but the leading term. So I'm just going to assume, instead of all 3 terms here, for my purposes, I'm going to sort of get rid of those. And just for now, all I care about is the leading term. Instead of messing with this whole thing, I'm just going to get rid of this stuff and work with the 2x squared. Now, I don't have the time now in this video to explain this whole principle of why we do the leading term and how it works. This video is made to explain to you how to calculate horizontal asymptotes, because it's not hard, and even the theory is not that hard, but I don't want to take the time to explain it. So the first step, so this is explanation of leading term. Reduce top and the bottom to leading term. And then you look at the top and the bottom and you see if anything cancels. And then set x to either plus or minus infinity. In other words, you're basically asking yourself, what's going to happen if I make x a really, really large number, either a positive or negative number? Once you do these three things, you'll know your horizontal asymptote. So let's take the problem we're working on and work through the steps for horizontal asymptote. So once again, here's this function. Horizontal asymptotes, I'm going to reduce to leading terms. Well, in the top, I only have one term, so there's nothing to get rid of. In the bottom, I have x plus 4, so I sort of eliminate the 4. So when I reduce to leading terms, I have 3x over x. Now, I go and I say, can I cancel anything? Well, in this case, I have x over x, which those cancel out. So when I cancel, I'm left with 3. Now here's a case where after I do the first two steps, there's no variables left. Okay, that happens sometimes. What I've done now, f of x is the same thing as y. This now is my horizontal asymptote. So it's interesting for this problem, horizontal asymptote, earlier we found the vertical asymptote to be x equals -4. If we were to try and create this graph, I'm not going to graph it. I'm just going to graph the asymptotes just so you see. Vertical asymptote at x equals -4. So you would do this. Horizontal asymptote at y equals 3. Then somehow you could figure out where your graph is. All right, I have like 4 more problems, and we're just going to step through these now that I've sort of described it. Maybe I'll just write this one as I want you to notice, because I'm going to talk about this later on. Look at this first problem we did. When we look at the leading term here, you notice the exponent's the same. I've got a 1 here and a 1 here. So you notice what happens when I ended up figuring out the horizontal asymptote. It was y equals 3. Look what I have here. The top leading term is x. The bottom leading term is x squared. So here's a case where the top is less than the bottom. Now let's see what happens. Let's first do vertical asymptote. I'm going to take the denominator, say equal to 0. If I want to solve this, I'm going to go ahead and factor this. This is a difference of squares. So when I solve this equation, I get x equals plus or minus 2. Those are now my vertical asymptotes. So I could say x equals 2, x equals -2. In this case, 2 vertical asymptotes. Once again, all comes from the denominator. For the horizontal, the leading terms, let me just write it all out to start with. This goes away, this goes away. I'm left with x over x squared. If I cancel, I'm left with 1 over x. So this is going to be my y, or this is going to be my horizontal asymptote. So the third step is, what happens when I put in a huge number for x? Just for fun. What if I put in 1 over 1 million? You know what that is? I think it's 0.0000. You know what this is? That's a really small number. And you know what? If I put an even bigger number in for x, this number gets even smaller. So normally what we do here, if our number is getting super small, you know what I'm going to call the vertical asymptote? I'm going to say it's approximately 0. So once again, if I were to graph these asymptotes, the verticals are at 2 and -2. The horizontal is at 0, so I try and draw it. You know, y equals 0 is the x-axis, so I draw it just above it. So there's y equals 0. This is x equals -2. So there are my vertical and horizontal asymptotes. Just out of interest, notice here, the leading terms have the same exponent. It ended up being 3 over 1, the coefficients. Here, you notice the top exponent was less than the bottom. Horizontal asymptote ended up being 0. And you know what? That's always going to happen. If you have a function where the leading term at the top is less than the leading term at the bottom, horizontal asymptote is always 0. It always works out that way. And if the top and the bottom have the same exponent, you know what the horizontal asymptote always is? It's the ratio, it's the fraction of the coefficient. And in a sense, we have 3x here, we have 1x here, it's 3 over 1. So you'll see that again in the final examples I do. How about this one? Y equals 2x squared plus 1 over x squared minus x minus 2. We're asked to find the asymptotes, both vertical and horizontal. Vertical, it's always the same thing. Take the denominator, set it equal to 0. This is a trinomial. Actually, it factors into x minus 2 times x plus 1. So when you solve it, you get 2 solutions, x equals 2 and x equals -1. Therefore, 2 vertical asymptotes, x equals 2, x equals -1. Horizontal, we'll reduce this down to leading terms. The top, you get rid of the 1. The bottom, you get rid of these 2. So you're left with 2x squared over x squared. Now when you cancel, x squared and x squared cancel out, and what are you left with? 2. Y equals 2 is the horizontal asymptote. Once again, look at my leading terms. The exponents are the same. That's just like that first problem. When this happens, the asymptote is going to be the ratio of 2, in this case 2 over 1 again. 2 more. Let's find the asymptotes for this. Vertical. Take your denominator, set it equal to 0. Once again, this factors x plus 3 times x minus 3. Two solutions. X can be plus or minus 3. Two vertical asymptotes. How about horizontal? So here's the case where if you get rid of everything but the leading terms, x cubed over x squared, cancel things out, you're left with x. So the third step is you plug large numbers in for x. So what if x was 1,000,000? You would have y equals 1,000,000. What if I put in 1,000,000,000,000 for x? Now, unlike the previous problem I did, when I put in larger and larger numbers for this x here, the answer got smaller and smaller and smaller, and it got really close to 0 and kept getting closer and closer to 0. Here, when I put in numbers, it just gets bigger and bigger. Now, an asymptote on your graph is where the graph approaches or gets close to a value of y. But in this case, y just keeps getting bigger and bigger. And that's why when this happens, you actually don't have any kind of horizontal asymptote. And look what happens here. Look at our starting problem. Look at the leading terms, x cubed over x squared. This is the first time we've had this where the exponent on the top is larger than the exponent on the bottom. Once again, it's almost like a rule. Whenever you have this, once you work out the horizontal asymptotes, it's always going to be this case. There isn't going to be horizontal asymptotes. All right, let me do one more example. And then hopefully you'll have a pretty good understanding of how to find these asymptotes. Last one, 2 over x squared minus x. Vertical asymptotes. Take the denominator, set it equal to 0. Solve it. Here I'm going to factor out. Looks like there are two solutions when x is 0 or x is 1. Therefore, two vertical asymptotes. For the horizontal, there's only one term in the top. The second term goes away. Here's a case 2 over x squared. What happens if I put in a really large or big number for x? This fraction gets really, really small. And once again, I go back to what I said before. When the bottom exponent is larger than the top, what's going to happen is you're going to have a horizontal asymptote of y equals 0. All right, so I hope that's clear of how to very easily calculate horizontal and vertical asymptotes. So hopefully if you see those kinds of problems on the test, you'll be able to easily calculate the correct answers.